Hello chemistry, welcome to class. Atif, I'm so sorry, even due to these circumstances you still have to hear my voice 3 times a day. I sincerely apologize that you have to hear me talk as much as I have to hear myself talk. We're going to go ahead and start with chapter 12 today. It's a fancy word. You can see it is stoichiometry or stoichiometry, I've heard it pronounced both ways. And we're going to start with kind of a little intro video.
Then a bit of permanganate, and now that we've got enough peroxide still left, you can see it's decolorizing straight away. That's pretty cool.
What's going on there, man?
So what's happened now, I didn't wash the thing out properly and we had some peroxide left, and now it's reacting faster than we can add the permanganate. That's pretty cool.
Okay, so what you saw was reaction. He was pouring that purple liquid into the clear liquid, and it was reacting. But the question I have, and the question maybe some of you have, is how long can it do that, right? How much of the peroxide in the clear solution, how much of that was left to be able to react with that purple liquid? Or in a simpler example, you know you can light a candle, but like, how much oxygen does a candle burn, right? If you just burn this whole candle, how much oxygen was used? We learned in chapters before that in order to burn something you need oxygen. Well, how much? And that's what this chapter is all about. How much of one thing do we need to react with the other thing to get like a final answer? And that is stoichiometry. The study of quantitative relationships between amounts of reactants used and products formed by a chemical reaction. Okay, so reactants used and products formed. We get the basic idea of this from that law of conservation of mass. Remember that mass can't be created or destroyed. It just moves around, right? We looked at that when we were balancing equations. If there's 4 ions over here, there has to be 4 right here. If there's 6 oxygen over here, there has to be 6 over here, because matter doesn't get created or destroyed in chemistry. So we're still taking that concept. We're just merging that concept of balancing equations as a conservation of mass with all the math we learned in chapter 11. Okay, so let's look at this example. That's what's happening here. Although this is happening really fast, this can also happen pretty slowly in the form of causing rust to form. But here we see iron burning with oxygen to form iron oxide. Okay, that would be like the word equation. But we know we can also say, like, well, this represents molecules and atoms, right? So this is 4 atoms of iron with 3 molecules of oxygen combining to form 2 what we call formula units of iron oxide, right? So that's how we would say it in those types of terms. Last chapter, we learned about moles and how these numbers can also represent the number of moles we have. So if we're looking at this example, we can say it's true that 4 atoms and 3 molecules and 2 formula units work, but we can also just say 4 moles of iron plus 3 moles of O2 combine to form 2 moles of Fe2O3. And remember, a mole is that gigantic number, 6.02 times 10 to the 23rd power. So these equations that we've been balancing since chapter 9, chapter 8, I'm not sure, are still coming into play because they still matter. Well, stoichiometry now is taking that one step further. What about mass? How much mass is 4 moles of iron? How much mass is this 3 molecules of O2? And that's the next step we're taking. So we're using the math from chapter 11, combining with all of the other balancing equations we've learned in the previous chapters, all into this chapter of chapter 12. So this is an overview of what I was just saying. We have the word equation. Iron and oxygen make iron 3 oxide. Okay? This is the balanced equation. This is talking about atoms, molecules, and formula units. Well, we also know that if it's a balanced equation, we can replace that with moles. But now, as I said just a moment ago, now we want to know about mass. Because according to the conservation of mass, all of the mass on the left side has to equal all of the mass on the right side. So then the question comes up, if we have 4 moles of iron, what's the mass of 4 moles of iron? Well, luckily, we spent all of last chapter learning that stuff. 4 moles of iron multiplied by the molar mass of iron gets us 223.4 grams. 3 moles of oxygen, of O2 specifically, multiplied by the molar mass of O2 is 96 grams. So we have 223.4 grams of iron on the left, plus 96 grams of oxygen on the right, combined to make 319.4 grams of reactants total. Well, let's see if that makes sense. Let's look on the right. If we have 2 moles of iron oxide, how much mass do we have? Well, we have to multiply that by the molar mass of iron oxide. And now you're thinking to yourself, I forgot how to find the molar mass. Well, remember, you can look on the periodic table for each of these elements, right? So let's go ahead and do that. So for iron, we know it's 55.8, and for oxygen, we know it's 16. Right? So there's 2 irons. So there's 2 times iron's mass, and 3 times times oxygen's mass, to get 159.7, I'm sorry. So 2 times that gets us 319.4. That is the same number as this. So we know we're following all of our laws of conservation, and the stoichiometric equations we have done all work out perfectly. Let's look at another example. Let's look at burning propane. Okay, so that you heat your home with that, you cook food with that, you can do some machining with that. So let's burn some propane, and let's see if it follows the law of conservation of mass. Now we know if it's a balanced equation, we know it's going to already, but let's prove that we know that by using stoichiometric calculations. So we got C3H8 plus 5O2 yields 3CO2 plus 4H2O. In this problem they gave you this. Hopefully you guys did not forget how to balance equations, because some of the homework problems you will need to balance them before we can even start. So we have a balanced equation, and the question is saying, well, how can you say this in terms of molecules? How can you say this in terms of moles? And how can you say this in terms of mass? So we have it here, but how can we say it in these 3 ways? Well, molecules is going to be really easy, because there's an invisible 1 right here, right? So there's 1 molecule of this, 5 molecules of that, 3 molecules of that, and 4 molecules of that. It's just the coefficients. And we see that right here. 1, 5, 3, 4. It's easy. That's all you got to do. Next up, we have the equation in terms of moles, which hopefully based off of last chapter, you also see this is really easy, because there's 1 mole here, there's 5 moles here, 3 moles here, and 4 moles right there. Right? So once again, right here, the coefficients tell you the number of moles. 1 mole of this, 5 moles of that, 3 moles of that, 4 moles of that. So far, so good. Now it's the new stuff. Now say this in terms of mass. How many grams of propane do we have? How many grams of oxygen? How many grams of CO2? How many grams of water? This is where we get to do math. Okay? So using the same kind of setup that we did last time for our last chapter, if I have 1 mole of C3H8 and I want to find out how many grams it is, I need to multiply it by its molar mass. How do I find the molar mass? Well, there's 3 carbons and 8 hydrogens, right? So there's 3 carbons, 3 times 12, and 8 hydrogens, 8 times 1. Add all that up, we get 44.09. So 1 times 44.09 is, of course, 44.09 grams. Now let's look at O2. 5 moles of O2 multiplied by its molar mass. Well, how do we find O2's molar mass? Oxygen is 16. So O2 means 2 times 16. So 2 times 16 is 32. 5 times 32, my dog does not like me talking about chemistry. 5 times 32 is 160 grams of oxygen. We do the same thing for CO2. 1 carbon and 2 oxygen. So 1 carbon, 12, plus oxygen, which is 16. So 12 plus 16 plus 16 gives us this 44.01. So since the problem says we have 3 moles of that, 3 times our molar mass gets us 132. We do the same thing for water. 4 moles times 18.02 grams of H2O over 1 mole of H2O gives us 72.08 grams of H2O. You are not done, right? Because we want the equation in terms of mass. So we would say there's 44 grams of propane plus 160 grams of oxygen yields 132.0 grams of CO2 plus 72.08 grams of H2O. In other words, if we added up the masses of the reactants, we get 204.1 grams of reactants. If we add all the masses of the products, we get 204.1 grams of the products. Therefore, the reactants and the products equal the same thing, so we can be sure that the law of conservation of mass is observed. And that's how to do these problems right here. Pretty straightforward. We actually haven't learned anything. We did this last chapter, so this is almost just like a little mini review of last chapter. This also is from last chapter, mole ratios. We're comparing a ratio between the numbers of moles of any 2 substances in a balanced chemical equation. This is incredibly important. This last part, a balanced chemical equation. You cannot just start making up mole ratios for no reason. First, you have to have a balanced chemical equation, and then you can find the mole ratios. Okay, so let's go ahead and just jump it right in this. In this example, we have aluminum reacting with bromine to form aluminum bromide. And we see this right here, this is happening. So what are the mole ratios? So that seems like an open-ended question that, like, well, I don't know, that could be a lot of things. And it can be a lot of things, but there is a finite amount. There is a definite amount. For example, if I said for every 2 moles of aluminum we have in this problem, how many moles of bromine do we have? Well, you would say that since there's 2 for this, and this is a balanced equation, that means there's 3 bromines, right? So we have this compound, or this ratio right here. For every 2 moles of aluminum, there's 3 moles of bromine. For every 2 moles of this, we have 3 moles of that. All we're doing is putting this over that. We can also compare, if we have 2 moles of aluminum, how many moles of aluminum bromide do we have? Well, we have 2. That's what that says, right? So we can just put 2 aluminums over 2 aluminum bromides. Okay, well now let's start with this guy. Let's compare this to everything. If I have 3 moles of bromide, how many moles of aluminum do I have? Well, 3 to 2. So 3 moles of bromide to 2 moles of aluminum. You see how this works? If I start with 3 bromines, and I want to compare how many aluminum bromides I have for every 3 bromines, I just look at this number, and that's a 2. So 3 bromines, 3 bromines, I'm sorry, for every 2 aluminum bromides. Then we can also, if you look, this right here is just the opposite of this, so we just flip it upside down, and that counts as another mole ratio, just flipping them upside down. And we can also just flip this one upside down, and we get this one. So if you compare all of them together and then just flip them all upside down, you get all the different types of mole ratios we can use in this problem. Let's look at another example. 2KClO3 breaking down yields 2 KCl plus 3 O2s. Alright, so for every 2 moles of this, how many moles of this do I have? Well, that's 2 to 2, right? That number is 2. That number is 2. So 2 to 2. What about KClO3 compared to oxygen? Well, that's 2 to 3. 2 to 3. And we do that with each compound. So that was just comparing KClO3 to all these. Now let's compare KCl to all those, and then compare O2 to all those. And then we get these two sets of ratios. So we have a total of 6 ratios. We don't know what we're doing with these yet, okay? So you might be confused, like, why are we comparing these right now? That's going to be incredibly useful for 12.2, but for 12.1, we're just learning how to do them, okay? So for these practice problems, all you guys have to do is determine the ratios here. So list all of the mole ratios. And then for number 3, all you have to do is balance it and then find the mole ratio. So a little bit more work, but not impossible. Everything in 12.1 we have done before. It just might not be in, I don't know why I was even saying that. Everything we've done in 12.1 we've done before. If you have any questions, please make it to the Tuesday and Thursday class times that we have going.